We carry supercomputers in our pockets and split atoms for energy, yet we maintain our oral hygiene using a remarkably primitive technology: physical friction. Standard toothpastes are formulated around volcanic-grade abrasives. You're effectively taking microscopic sandpaper and grinding it against your teeth to scrape dirt away. But those stains from coffee, tea, and food aren't just sitting loosely on the surface. They are fused to your enamel by an invisible, protein-based molecular glue. This is the core paradox of oral care. We have been applying a macroscopic, mechanical solution to what is strictly a microscopic, chemical problem. When you try shattering chemical bonds with sheer physical force, the result is unintended collateral damage. Over a lifetime, that abrasive friction erodes the microscopic landscape of the tooth, thinning out the irreplaceable enamel layer that your body cannot naturally regrow. Increasing the physical force of your brush won't break the chemical glue holding the stain. It only accelerates the permanent destruction of the tooth itself. To protect the enamel, we have to abandon the sandpaper approach. We need a molecular scalpel. Dissolving that protein glue requires a protease, a specialized enzyme designed to target and disassemble protein structures on contact. But the human mouth is a volatile environment. Constantly shifting pH levels and temperature spikes from hot coffee or cold water cause standard enzymes to denature or melt, rendering them useless. To find biology resilient enough for this environment, researchers turned to the Geozyme hot springs in Tibet, one of the most hostile geothermal sites on Earth. The thermophilic microbes surviving in these boiling pools have evolved immense structural rigidity. Their biological tools are built with the reinforced architecture needed to function where most life simply disintegrates. By harvesting these evolutionary survival traits, science can build a tool for the mouth that remains stable under extreme conditions. Finding a specific, useful enzyme within millions of microbial sequences is the great bottleneck as biotechnology. Using traditional methods, it is a search that usually takes decades of manual testing. To solve this, ScioMicro utilized deep learning models built for protein structure prediction, the same computational breakthrough recently recognized with the Nobel Prize, to scan 20 million genetic sequences for a molecule with atomic precision. The AI successfully isolated one specific high-performance sequence, Geozyme. This technical breakdown shows a broad plateau of activity between pH 4 and 7, exactly where standard enzymes lose structure. Its thermal endurance is equally striking, peaking near 50 degrees Celsius, heat that would instantly destroy conventional biological agents. Geozyme is a precision-engineered software update for human hygiene, a molecule computed for maximum utility in a volatile environment. Upon contact with a tooth, Geozyme ignores the inorganic enamel entirely. It acts as a biological scissor, identifying and snipping the specific protein strands holding the stain. It releases the bond without the need for physical abrasion. A manual brushstroke happens about 5 times per second. It is a slow, macroscopic action. Geozyme, however, executes 317 precise molecular cuts every single second. True cleanliness is achieved not through the mechanical friction of our muscles, but through the microscopic frequency of enzymes. To prove this efficacy, researchers saturated biological tooth models with a stubborn, dark blue protein pigment to establish a severe baseline of discoloration. After 5 minutes of exposure to a Geozyme solution, the pigment bounds begin to fracture and fade. Within 1 hour, the protein glue is entirely dissolved. The tooth returns to its pristine white state with zero enamel wear. The era of brute force oral care is ending. We have learned to harness the ancient resilience of volcanic biology, guided by modern AI, to replace friction with absolute molecular precision.